Now, something that we're going to find with epithelial tissue, do you guys remember the cell connections? Did y'all talk about those any at all? They're going to be found. And yesterday, I tried, when I was drawing the picture, I did a little mark between the sides of the cell and the base of the cell. The connections are going to be found on the basal and the lateral surfaces of the cells. Now, what's their job? Why do we need to have these connections that are existing? Why do I have to have them?
Communication.
Well, we could have it for communication, maybe passing a substance, okay? Anything else you might think of based upon where we find epithelial tissue? Because skin, lots of areas to the exterior of the body. We're kind of needing to keep stuff protected, stuff waterproof, okay? So the connections that we have, look what they can do. They can create connections cell to cell by way of the sides. They can create a connection by way of the base to the basement membrane. Now, the type of connection determines what is it doing. So if we look, we have what's termed desmosomes, okay, tight junctions, and then gap junctions. What they're doing, they're helping the permeability, whether that needs to be present or well controlled, okay? Holding the cells together. In areas where we find epithelial tissue, some of these cells need to be held tighter together than others. Mechanism for cell communication. So this is what we're going to see happen with these different types. So if we look at the connections, a desmosome, disc-shaped, areas subjected to stress. Now let's go back. Look at that picture. Hemidesmosome. That thing got a hemi? Y'all remember that? Okay. I never knew what hemi was. Okay. So I finally looked it up. Hemispherical. All right. Half. But we said that it is a desmosome. But here I'm seeing hemidesmosome. Where would my other half be? In the basement membrane. And look at all of these little strings sticking out from it. The filaments, okay, like the cytoskeleton, okay? Note we've got some that extend in this direction, some that extend in this direction. And if we had desmosome, we would have it going like that in opposite directions. What kind of connection do you think that would create? One that's kind of tough, very tough, not tough at all. Very tough, okay? It would be difficult to pull that apart. So if we think about desmosome, these are going to be found in cells subjected to stress. What kind of stress? Oh man, Dr. Young's class, her class just stresses me out. I can't handle it. You know, where in the world does that woman come from? That kind of stress? Mm-mm. Or maybe movement. Maybe. Okay. That type of stress? Mechanical, maybe? Okay. So it's going to be found areas that are going to be subjected to stress, but we need to make sure cells don't do this number. Okay? But they stay close together. Look at what they've got. Adhesive glycoproteins. Adhesive, kind of cool. Okay? Glyco's telling me what? Sugar to a protein. The filaments I just mentioned, parts of like the cytoskeleton, and we see this epithelium of the skin. Do we put our skin under stress? Yes. Okay. There are other ways too. The Hemi kind of pointed out, half on one side, half on the other. The other type of junction, a tight junction. Okay, what's the difference? If we come over here, note that on this lateral surface, on the sides, this is where we find a tight junction. Does it look like something is really going to get through that? Does it look like we're going to really see some of that cell pull apart from each other? Or from the other cell, I should say. No. So, tight junctions help to hold the cell together, form a permeability layer. What exactly does that mean? Permeability is telling me what about movement? Stuff to go back and forth. So it's going to be something that's going to control some of that. We have two zones. That's just simply what this is telling me. Zonula adherens. My zone of adherence. Zonula occludens, my zone that occludes materials. So the zone that adheres, it's like a weak glue, holds them together. We're going to see it in simple epithelium. The zone that occludes, this one affects my permeability for those cells. Good examples, stomach, urinary bladder. The stomach, we don't want the acid from the stomach leaking out. Is that correct? Urinary bladder. We don't want the urine leaking out of the bladder. So it helps form permeability layers. The last type of connection is a gap junction. When we look at the gap junction, just like the name implies, there's gaps that are present. This means something can move between the cells. So we're going to see they are little protein channels. They're going to allow materials to move from one cell to the next. One of the biggest places that this becomes important in our bodies, cardiac cells. This ability for the ions to pass between the cardiac cells is the reason the heart beats. We look at the heart beating and we think it's one movement. It's not. It's every single cell working individually to allow the passage of the materials, and each cell has such a good coordinated effect, it looks like the heart beats as one unit, but it's not. It's really interesting. So, basically communication between those cells. Now, under the epithelial tissue, another part that we get, that it forms, are glands. And glands get a little bit interesting. They're going to be epithelial tissue with some connective tissue that we haven't talked about yet. Okay? The two types, endocrine, exocrine. Endo means inside. So there is no duct leading from that gland. Okay? Good example, hormones. We're not seeing a duct lead to the outside of the body. So the product stays inside the body. Therefore, a huge area of the body that we call the endocrine system. Hormones. Love that system. It is so interesting. Exocrine. There is a duct that leads to the outside of the body. We're going to classify exocrine glands according to what is their structure or what is their method of secretion. What in the world does that mean? A method of secretion? It's really interesting. If we classify them by structure, we're going to say it's unicellular, one cell. These are our goblet cells that we find in that pseudo-stratified columnar. The goblet cell is one cell and it produces and secretes the mucus. Everything else we're going to see for glands, what kind of glands lead to the outside of our bodies? Sweat glands. Oil glands. These are multicellular glands. And their method of secretion, oh yeah. So, multi-celled exocrine glands. The ducts that are present. Let me come over here and look at this. Up here in this picture right here, these are simple glands. Can you take a guess as to why they classified them simple?
Few branches.
There you go. And if you look at the picture, we don't have a whole bunch of branches that are present. They're multi-celled because they're trying to show you all of the cells that are present making up that duct. Does that make sense? Now, down here, compound. A little more difficult, right? I think so. Because I've got branching here, I've got branching here, I've got branching here. Branching that leads to another little bulb, bulb, okay? Products that are going to get produced in the bulb, secreted out. Does that make sense? Okay, so the ones that are more complex, we're going to find them, look at the areas, part of the digestive tract and part of the respiratory tract, respiratory system. Kind of interesting, okay? Their product, now, product, for example, in the pancreas, that's going to be a digestive enzyme that'll get produced and put into the body. It's actually leaving the pancreas, but it's not leaving the body. But it's still considered exocrine. When we look at a sweat gland or an oil gland, the product actually leaves the body. Okay? Now, if we look at how they secrete their materials, what do you notice as a difference between these three pictures right here.